Hey there, and welcome. So, today we're going to tackle systems of nonlinear equations. I know, that sounds super intimidating, right? But what if I told you it's the math that predicts where a comet will cross a planet's orbit? Or, hey, even the exact point where a business finally turns a profit. This is all about where things connect. So let's dive right in. So, let's kick things off with a pretty cosmic question. Picture this. You're an astronomer, you're tracking a comet's path, which is an ellipse, and you're also tracking a planet's orbit. How in the world do you figure out if, and more importantly, where those two paths might intersect? This isn't just a thought experiment, it's a real-world problem, and getting it right is, well, kind of important. At its heart, the idea is actually super simple and kind of elegant. Each of these paths, the comets and the planets, can be described by an equation. So when we're looking for that collision course, what we're really doing is searching for a single point in space, a set of coordinates, that solves both equations at the exact same time. Okay, so here's our game plan for today. First, we're going to talk about what makes these curvy equations so different from the straight lines you're used to. Then, we'll get our hands dirty with two really powerful methods for finding those meeting points: substitution and elimination. And finally, we'll zoom out and look at what happens when the answer isn't just a point, but a whole region of possibilities. All right, let's take our first step, moving beyond straight lines. Look, we all get linear equations, right? They're predictable, they're straight, but the real world, it's messy. It's full of curves and arcs and orbits. And that's where the really cool math of nonlinear equations comes into play.
So what even is a system of nonlinear equations? Well, it's pretty much what it sounds like. It's just a group of two or more equations where at least one of them isn't a straight line. It could be drawing a parabola, or a circle, or that comet's elliptical path we were just talking about. The whole puzzle is finding the exact points that make all the equations in the system true at the same time.
Our first tool for solving these should be a familiar one if you've worked with linear equations before. It's called substitution. And I like to call it the plug-and-play method. It's really all about taking one equation, solving for one variable, and then plugging that piece right into the other equation. Simple as that. And this is where things start to get really interesting. See, with two straight lines, they can cross once or not at all. But when you have a line and a curve, say a parabola, suddenly you have more possibilities. They might miss each other completely, no solution. Or the line could just barely graze the parabola at one single point. Or it could slice right through it, giving us two intersection points. And the process? It's a pretty straightforward four-step deal. First, you solve one equation for one variable. Second, you plug that expression into the other equation. Third, you solve the new equation you just created. And fourth, you take that answer and plug it back in to find its partner. Seriously, just keeping your work neat is half the battle here. Okay, theory's great, but let's put this method to the test with an example. So in our system, we've got a straight line, x minus y equals -1, and we have a parabola, y equals x squared plus 1. The question is, where do these two actually meet? Okay, so first things first, we're going to take that simpler linear equation and rearrange it to get x all by itself. That gives us x equals y minus 1. Now for the plug-and-play part. We're going to take that whole y minus 1 expression and substitute it right into the x spot in our parabola equation. So after we substitute, we get y equals the quantity y minus 1 squared plus 1. When we expand that out, we get a quadratic equation, y squared minus 3y plus 2 equals 0. Now that looks scary, but it factors really nicely into y minus 1 times y minus 2 equals 0. So our y values have to be 1 and 2. We plug those back into our simple equation, x equals y minus 1, and we get our final answer, the two intersection points, 0, 1 and 1, 2. Boom. But what happens if both equations are really complicated? When trying to isolate one variable just looks like a total nightmare? Well, for that, we've got another amazing tool in our toolbox, elimination. I like to think of this as the stack and cancel method. And trust me, you're going to need it. Because when you start dealing with two curves like a circle and an ellipse, the number of possible intersection points just skyrockets. They might not touch at all, or they could intersect at 1, 2, 3, or even 4 different points. Trying to use substitution here would get really messy really fast. So let's check out this system. We've got a circle and an ellipse. But notice something. See how both equations have an x squared term and a y squared term? That right there is a huge flashing sign that tells us elimination is going to be our best friend for this problem. So here's the strategy. We need to make one of the variables cancel out. To do that, we're going to take that entire top equation and multiply it by -3. Why? Well, it's a totally strategic move. It turns that x squared into a -3x squared, which is the perfect opposite of the 3x squared in the bottom equation. We're setting them up to be eliminated. And now for the fun part, we just stack the two equations and add them together. And just like we planned, the positive 3x squared and the negative 3x squared cancel each other out completely. Poof, they're gone. And look what we're left with, a much, much simpler equation to solve. 22y squared equals 22. Solving 22y squared equals 22 is a piece of cake, right? Y squared equals 1, so y has to be +1 or -1. Now, we take both of those values and plug them back into one of the original equations. We find out that for both of them, x squared equals 25, meaning x can be +5 or -5. And that's how we end up with 4 distinct intersection points. Elimination just made that whole complex problem so much easier. Okay, so far, we've been on a hunt for these very specific points where things cross. But what if the answer we need isn't a single point? What if we're looking for an entire range of answers? Well, that's when we level up from equations to inequalities, and we go from finding points to shading in entire regions. I mean, think about it. What if you want to know the range of prices that will actually make your business a profit? You're not looking for the one single break-even point. No, you want the whole zone of profitability. That's exactly the kind of question that inequalities are built to answer. And when you're graphing these, the line itself tells you a big part of the story. If you see a dashed line, that's a signal that the points on the boundary itself are not included in the solution. But if you see a solid line, it means that boundary is included. It's a simple little visual clue, but it has a really important meaning. Now, when you have a whole system of inequalities, the process is really visual. You graph each one and shade in its solution area. And the final answer, the solution to the whole system, it's the one spot on the graph where all of those shaded areas overlap. We call that the feasible region, and it's basically the sweet spot where every condition is met. So let's wrap this all up. Nonlinear systems, they're for finding where curvy paths cross. Substitution is your go-to method when one variable is easy to get by itself. Elimination is an absolute powerhouse when you've got matching terms you can cancel out. And inequalities, they take us beyond single points to find entire regions of solutions. And if this all still feels like a bit much, just remember this. The methods we use today, substitution and elimination, they're the exact same tools you use for simple straight lines. You haven't had to learn a totally new kind of math. You've just learned how to apply what you already know to much cooler, more interesting shapes. So I'm going to leave you with this question. Now that you know how to find these intersection points, what does that open up for you? What real-world orbits or project paths or business models could you analyze now in a way you couldn't before? Because once you can solve for the meeting points, honestly, the possibilities are endless.